the chemical properties of an element is its electronegativity. And what electronegativity is when an atom is bonded to another atom. And that's a key part of the definition. When the atom is bonded to another atom, the electrons that are between those two atoms forming that bond, both of those atoms have an attraction for those electrons. And what the electronegativity is a measurement of how strong that attraction is that each particular atom has for those electrons in that bond. So it's kind of like it's a measurement of tug-of-war strength, if you will, where the electrons are the tug-of-war rope and the two atoms are the two teams. So it's a measurement of which team has the stronger pull on the electrons. If we take a look at how electronegativity changes as we move about the periodic table, we can see from this graphic that as we move from left to right across the periodic table, the trend is the same as we saw for first ionization energy when we looked at those periodic trends. With that one, the amount of energy it took to remove the most loosely held electron increased the closer we got to the noble gases, and also the smaller the atom was, the closer into the nucleus that the electrons were, so closer to the top. And the same is true for electronegativity. The closer you are to the nucleus and the closer you are to the noble gases, the stronger the attraction is going to be for additional electrons. And that's what electronegativity is all about, attraction for electrons in a bond. So your greatest electronegativity values are going to be found in the upper right corner, with fluorine being the greatest electronegativity. And the least electronegative elements will be found towards the lower left of the periodic table. So your most active metals, such as cesium and francium, those are going to have the lowest electronegativity, or the lowest attraction for electrons in a bond, because they, like most metals in general, are very eager to give up electrons. So the last thing they want to do is attract further electrons. They would have a lower ionization energy. Consequently, fluorine is a rather small atom in size, plus it's right next to neon, and so it needs one more valence electron to complete its octet. Notice that the noble gases are not present on this chart, and that is due to the very definition of electronegativity. An atom or an element can only have an electronegativity value if it forms a bond, and the noble gases, as a general rule, are fairly inert. They're non-reactive. On some sources, not on this one, but on some references, you may actually find electronegativities for some of your heavier noble gases like krypton and xenon, because they have had compounds that have been artificially created in a laboratory, but not for any of your lighter noble gases, helium, neon, argon. They have no compounds that are known, and so therefore they cannot have an electronegativity value. Now these electronegativities are important because these are going to help determine how the atoms are going to react with one another, what kinds of bonds they'll form, and once we get past the idea of bonding, then we can look at the compounds that they form and the characteristics of those compounds, and those translate then into the properties of the substances that we can interact with and observe on our scale. So when we look at the electronegativities, again, use the analogy of a tug-of-war. If you have two teams and one team has a much higher, much stronger pull on the in the tug-of-war match, then they're going to win, and they're going to pull the flag completely over to their side and be declared the winner. So when we're talking about atoms and their electrons, if there's a large electronegativity difference, one atom has a much higher electronegativity than the other, then that atom is going to win the tug-of-war and totally win over the electron or electrons from the element that has the lower electronegativity. And so when that happens, we have a complete transfer of electrons. This creates electrically charged atoms, or ions, and once you have those ions created, now you have particles with opposite charges. That electrostatic attraction, opposites attract, takes over, and that's what holds those particles together in a compound, and so in that bond, and so we call that an ionic bond because it's forming ions. Conversely, if we have two atoms that have relatively the same electronegativities, or at least closer to one another, a small difference between them, then you may have one atom that is dominating the tug of war, but it's not dominating so much that it's completely won the electrons over, that it's completely won the tug of war match. And so while it may be winning, it hasn't totally ripped the electrons away from the element that has the smaller electronegativity. So the two atoms are still sharing the electrons, and whenever we have a sharing of electrons, we refer to this as a covalent bond. Now the question that arises next in looking at this is, what's the difference between a large electronegativity difference and a small electronegativity difference? What's the borderline? What's the number that we look for when we subtract the electronegativities to determine which kind of bond we have? The number that we're going to use as our division between what's ionic and what's covalent is 1.67. So when you look at a source, whether it's the graphic that we looked at earlier, whether you look in your textbook, whether you look online, you might find a little bit of variation in the number of decimal places or significant digits that are reported, but in general, the number that we're going to use is 1.67. So when you take the two elements that are bonded together and subtract their electronegativities, if the difference comes out less than 1.67, then we classify the bond as being covalent. There's a small enough difference that, for the most part, the atoms are simply sharing their electrons instead of having them transferred. If the difference is greater than 1.67, then that means that one of the atoms is clearly dominating the other. It has a much higher electronegativity, sufficient enough that it is able to remove the electrons from the other atom and take them on as its own, thus forming ions, and hence we would classify the bond as an ionic bond. And it's important to note that this idea of covalent and ionic, it's not a black and white issue. It's not 100% covalent, 100% ionic, and that's it. Its bonds are on a continuum. And it's a continuum of how much covalent characteristic do you have, how much ionic characteristic is there to that bond. And that 1.67 value represents the 50-50 mark. At a difference of 1.67, the characteristic of the bond is half 50% sharing characteristic, 50% complete transfer. So that would be the line that would declare the winner, if you will, in our tug of war match. Now within covalent bonds, we can further classify those as nonpolar covalent or polar covalent, and we'll get into that in a future lesson.